Hey everybody, welcome back to Calc 3 Online. So the plan for today is just do a few review problems from chapter 16 here. And there's so much stuff in chapter 16, it's hard to pick out just a few problems that really highlight the important stuff, but I think I did it. So this first problem just says find the net flux of, given this vector field here, through a cube in the first octant with these vertices. So basically the unit cube. So this picture you got here, like x, y, z, right? This unit cube right here. And what I want to stress is, so if we're going to do the net flux, we basically have to check out, the connection between this vector field and every single surface, right, on this cube. And there's 6 of them, right? So, I don't know, take like this one right here. Basically, you'd have to get, that's the plane z equals 0, the bottom of the cube. So you would have to find like a normal vector for everything, right? A unit normal. Now, here it's actually not that bad, right? You can just do the vector that points like straight down. So 0, 0, negative 1. But then you'd have to do like f dotted with n and all this stuff, right? It's 6, it would be a lot of work because it's 6 surface integrals that you would have to do separately. And then you would add up each one, right? You'd have like a double integral, with a dot product in there. And then you'd add to it again, another one with a dot product, and you add to it again, right? But the power of the last thing I taught you, the divergence theorem, is that if you ever have one of these objects, like one of these, what they really call a simple solid, like a cube is a simple solid, spheres, tetrahedron, stuff like that, then you can just use the divergence theorem. And so this problem that becomes like super cumbersome, where you have to do this for every single side, simplifies a ton. So this is actually how I would do the problem, and how I would hope you would do the problem too. One of the harder things I think in this unit is to know when you can use what tools, right? So this divergence theorem thing that equates the surface integral across the simple closed object to this triple integral, you can just use that whenever the partial derivatives of this thing is well defined and the object is one of these simple closed surfaces. So, with the divergence theorem, this thing is like over before you even know it. Basically, right, the divergence of f, just the, partial of 2x with respect to x, so 2, plus partial of y with respect to y, which is 1, plus partial of 4z with respect to z, which is 4. So you get 7. And then you're just literally doing a triple integral over that cube of now just 7 dv, right? And it's a cube, so you don't need to do any changing of coordinates or anything. You just do 0 to 1 for every single bound. Call it, dxt, y, dz. This, a super nice integral because basically the 7 is going to pull out. You're just going to multiply it by 1. So yeah, you get 7. So this problem is like super, super, super fast with divergence. And I really suggest that when you start getting into like the real world with math and science and things, you think about what tools do I have at my disposal. Math classes, like up to this point at least, are basically just teaching you tools. And this is a theorem that equates 2 types of integrals, but it's really just a tool that like lets you do these surface integrals way faster. It's a time saver. All right. Another thing that just definitely want to know from this unit is curl. So I just want to literally go through another computation of curl here. So curl again can be written as this del operator crossed with f, and we just do it with a cross product, right? ijk. And then it's a little weird, but you put in the vector that goes here is like the del operator, which is just like a vector of just the partial derivatives. So we have partial with respect to y, z, and then we put in, f, the vector field here, x squared y, x, y, z, minus x squared y squared. And then, now you just compute the cross product. Same old thing where you to do the first one, you blank out these two, you multiply these, and then subtract these, right? And if you go through and do that on this one, I'm just going to do it as a column vector. You'll get negative 2x squared y minus xy. And then you'll get 2xy squared, and then yz minus x squared. And that's it. So curl is a vector and follows, the right-hand rule kind of stuff. Very, very, very common in a lot of electricity and magnetism stuff, just tons of areas in kind of physics and engineering and things. It's a very common just vector operation that you want to make sure you know. Divergence, on the other hand, is not a vector, right? This thing is a scalar. And basically the way we do this one, right, is we just take I basically did it over here, but we just take the partials and just add them all up together, right? So in this case, and here the symbol we can use is the del operator dotted with f, right? And so we would just get partial of, this first component with respect to x, plus this one with respect to y, plus this one with respect to z. So we'd get 2xy plus xz minus nothing, right? And so what you can think about here is that this thing is now giving you a function that basically you can evaluate, right? Like you could plug in, let x equal 1 and y equal 0 and z equal 2 or something. And, at that point, right, you're going to get, what would you get? You get 0 plus 2. You get 2. And so then we're basically thinking, okay, at this point 1, 0, 2, a divergence of 2 means that at that point there is more stuff leaving the area than coming in. And so we analyze these in a sense kind of sinks and sources. So where is stuff coming from? That's kind of a source, and a sink is where it's going. And so if more stuff kind of goes in towards a point, then there's a negative divergence, right? It's not diverting out. But if it's positive 2 here, then there's a positive measurement of stuff, in a sense, leaving the area. And that stuff can be really abstract. It can represent all sorts of different things. So just another really, really, really important vector operation that you want to know. All right. So this problem just asks you to evaluate this line integral, okay, where C is the boundary of the region R between the quarter circles of radii A and B, centered at the origin and contained within the first quadrant. So this is another example where you could just try to jump in and start doing the line integral. But, a lot of this unit I've just been showing you guys how we can use different theorems and different tricks and stuff to simplify some of our computation. And whenever you see this setup, okay, you got this line integral, and C, the curve, really, again, they should really be called curve integrals, but that we're integrating over, is the boundary of a two-dimensional region. That is exactly what Green's is kind of good for. If they were talking about the boundary of a surface, then, which, a planar region is a surface, but if they were talking about more kind of the standard surface, like a sphere or something, then that would be like a Stokes problem. And remember, Stokes is really just generalized version of Green's. Green's is like a special case of Stokes. So really they're kind of the same thing. But I would basically try and set up a Green's theorem problem, because if I can do Green's, probably going to be way easier. So I'm going to start off and just draw what we basically have happening. We know we're in the first quadrant, and we're told that there's these quarter circles, okay? And so what we're basically saying is that we want to integrate, this kind of region. The radius of the inner one is like A, and the outer one is B, right? And Green's theorem just says that that line integral should be equal to the double integral of q with respect to x minus p with respect to y, just like dA, right? And so here, like q with respect to x, q is this whole thing in here, right? And if you just do the integral of that, or the derivative of that with respect to x, right? This goes away, you get 6x. Where is it? Yeah, 6x. And then p with respect to y is just nothing, right? There's nothing there. So there's nothing in regard to y, everything's constant. So you have minus 0, just like dA. And so literally, you've just taken a line integral, and you've made it into a really, really simple double integral now, right? And if you were going to do this double integral, right, we're looking at this region right here, we should, I would convert to polar, because it's a perfect setup for polar, right? So converting to polar, you're going to have 6r cos theta, and then you'll have to multiply by the Jacobian, r dr d theta. dr is running a to b, and theta is going 0 to pi over 2. And so now you can just go, it's actually a really nice double integral, right? If you solve that thing out, you'll get 2b cubed minus a cubed. So there you go. Definitely an example that's way easier to do than having to deal with trying to solve this line integral out by hand. One thing, too, that is definitely worth noting, so we sort of assumed that the orientation of this thing was the positive counterclockwise orientation that I'm drawing out here. If it wasn't, right, there's going to be like a sign change to the problem, but assuming that this is the path that we were taking, and that's the kind of thing that really, like, the problem should state, like, more clearly that, like, you're going in the positive orientation along the curve like that. And then in that case, all the signs work out the way I did it. It's like the positive case. But if it's the other direction, you're just going to get a negative. All right. So this is, this problem says let S be the part of a paraboloid given by that, right? Where z is greater than or equal to 0, and let C be the trace of S on the xy plane. And the question is asked to verify Stokes' theorem for the vector field 3z, 4x, 2y. All right, so let's start with doing the line integral around the curve C of f dot dr. So, Stokes again says that this line integral should equal the surface integral, right? Like the flux across the surface in question, right? That has that boundary curve. And so we're going to have to do a line integral and a surface integral, and then hopefully get the same answer. That's the idea. So the line integral is just for the, it says let C be the trace of S on the xy plane. So if you have a paraboloid, right, upside down one, like this, the trace that they're talking about is like the disk, like, well, just the outer edge, right, of that disk. So this. And that is, just a circle, because this is just an upside down paraboloid, nice circular paraboloid. That disk is just going to be a circle, and could be parameterized with, standard sine cosine stuff. So it's a circle of radius 3, right? Because of the 9 right there. So I would just let x equals 3 cos t, y equals 3 sine t, and then z would be 0, right? Because we're in the plane, the xy plane. And so when you do these line integrals, right, you got to parameterize. So you do like f of r of t. So this is my r of t, right? And so given my f, my 3z, 4x, 2y, I would get 3 times 0 is 0, 4 times 3 is 12 cos t's, and then I would have 6 sine t. And then we have to do r prime of t, supposed to be a t in there. That's going to be minus 3 sine t, 3 cos t, and then 0. And then to do these line integrals, right, we can just do the dot product of those two things. We just do, the integral f of r of t dotted with r prime of t dt. And so if you do that out, it's quite a nice dot product because you get 0 and 0. So this is the only thing that contributes. We are going a full 2 pi around, in a circle. And we go 3 times 12 is 36 cosine squared t dt. And to do that out, I would just switch it to the, you can like swap out cosine squared for the 1/2 1 plus cosine 2t. So 1/2 of 36 is 18, and then you'll just have that multiplied by 1 plus cosine 2t. All nice integrals from there. You get 36 pi, I'll just tell you. So that is the line integral, right? And so now you have to switch gears, and you got to do a surface integral. And the one that we specifically do is it's a double integral, right, of the curl of f dotted with n ds. That is how you do these surface integrals, okay? So the surface in question is this paraboloid, and we've talked about this before, but like you could kind of think for any surface, kind of think of this patch, right? And we've talked about how you can like get the area of like a patch on a surface by doing this like a cross this like vector across this vector, and then doing the finding the magnitude of that and dividing out by that to get the normal. And so that's that cross product. Let me just explicitly write. So this unit vector n, right, would just be like given by a cross b over the magnitude of a cross b. We've done this before multiple times in other videos, but the way I built it up was, I think, first done when we did like surface area or something like that. But generally speaking, a cross b is like minus f with respect to x, minus f with respect to y, and 1. If you have like z equals g, a function of x and y, let's say, or f, sorry, yeah, that's fine. So basically we have a function of just x and y here, right? And so we can use this kind of nice shortcut. This is something that we've seen before. So my normal would basically be this divided out by the magnitude. And so what that would look like is, so 1 over, we'll do the magnitude here in a second. The vector is minus f with respect to x, which is going to be, this is my function. So I have minus 2x, so positive 2x. And then minus this thing with respect to y, which is, again, just like a 2y double negative thing. and then a 1. Right? And so then these are what I need to put in here, do the square root of those things squared. So I get 4x squared plus 4y squared plus 1. Okay? So all of that just to get the normal vector to that surface. So, given a point now on this surface, any xy, this represents the normal of that. Right? We also need the curl of f. Okay, so I think I'm going to have to go to a new page here. But the curl of f is just, of course, I hat, j hat, k hat, partial x, partial y, partial z, and then we got 3z, 4x, 2y. And if you do that out, you get actually just 2, 3, 4, which is quite nice. All right? And so then we have to dot product these things, okay? And so if you do double integral curl of f dotted with n ds, you're going to get double integral 4x plus 6y plus 4, right? And I'm just literally dotting 2 times 2x is 4x, right? 3 times 2y is 6y, and so on. And then there is still this magnitude that's tacking along here. And then, if you just kind of remember the general kind of idea with these, since double integral of g of x, y, z ds equals double integral g of x, y, f of x, y, which is the situation we have, right? Then there's this magnitude of a cross b in here, and then dA, this whole thing was what ds is. It's nice because the square root will cancel with that, right? And so the square root part goes away, and you literally just have to do the double integral of 4x plus 6y plus 4, and then dx dy. And, well, let's say dA for a second. So the region, right, that we're integrating over is still that circular region. And so the problem is best switching to polar again. So I would switch to polar. Your radius is 3, and the angle rotates full 2 pi. And so then we have to put in, r cos theta there. We put in r sine theta there. And then multiply by r dr theta. And actually a fairly nice integral, no really weird tricks. You will get 36 pi again. So this is one where I think the surface integral is actually harder than the line integral. But there are times where it goes back and forth. There's times where the surface integral is easier than the line integral too. So you might want to do it that way. But sure enough, 36 as a surface integral and 36 as a line integral. Both of them work out. And so Stokes' theorem is verified. That's the idea. So you definitely want to know from this unit all the major theorems. I didn't do one here of the fundamental theorem of line integrals, but that's really important too. We've got that one. We've got Green's. You should know the different vector forms of Green's. There's 2 of them, right? One with divergence, one with curl. We talked actually about before how this this structure is really just the higher dimension up version of the curl formulation of Green's. And so that's important to know too, the connection between Stokes and Green's, and how Stokes is a higher dimension up version of Green's. And then of course you should know the divergence theorem. Super, super handy and a neat application of triple integrals and things like that. So lots of stuff in this unit, lots of big theorems, and if you keep going into the more like applied side of math, you tend to use a lot of these theorems. They show up time and time again, so very good things to know.